So can people from online hear me? Okay, good. Let's wait 1 more minute to start. Yeah. So today is Friday, so I think nobody's like coming to school. Uh, so please move forward if possible. We do have some people joining us from online. So let's start once you are seated. Uh, all right, uh, let's start today's lecture. So today we are going to continue our learning journey about levels of testing and test automation. So in our last lecture, we have learned different two levels of testing, unit testing and integration testing. Today we are going to learn the third level of testing, which is system testing. And after that, we are going to learn some test automation technique, which could be useful in practice, and it will be covered by assignment 2 as well. So before we jump into today's topic, let's have a quick recap of what we have learned so far. So in our previous 2 weeks, we have learned functional testing and structural testing, which are both related to how do we design test inputs or how do we design a test suite. And we just learned levels of testing in our previous lecture, which is about how do we determine the testing targets. For example, we can select functions as our testing targets. We can combine functions into some subsystems as the testing target. And of course, we can use the entire system or the entire software as our target for testing. And in our last lecture, we have learned unit testing, which is normally done by the developers and during development. And we have also learned integration testing, which is about how to build different integrations or different subsystems. And now we are going to learn system testing. And system testing could be either functional or non-functional, as we will learn later. So these are roughly our plan. So we have learned these functional and structural testing in week 2 and week 3. And in this week, we learn levels of testing and system testing. And here comes a definition again. So system testing is about testing the entire system or the entire software. So the key word here is that we are testing the completely integrated products, and we are testing with specific requirements on functional or non-functional aspects. So system testing could be both functional or non-functional. And here the functional and non-functional is a little bit different from the definition of functional versus structural. So non-functional doesn't mean it's structural, and we will learn some non-functional properties of programs today. So, so about among the three different levels of testing, the system level is actually closest to our everyday experience because we are using the end products, not just functions or some combinations of small different functions, right? So this is like we are testing from the user's perspective. And for functional system test, what we care is about the features or the business logic of the program. So we target to test whether the system can function well or not. And the method is normally that we provide some test inputs, we validate the outputs of the program with some expected results. And for non-functional aspect here, it's not like we are focusing on the source code, we are focusing on the code structures. Instead of that, we are actually, this one is blocking. So we focus on some non-functional features rather than, like structural aspects. So instead of focusing on the business logic or the features of the program, what we test for non-functional system testing is we test for the performance of the system, we test for scalability, usability, and some other quality attributes. And the method is normally to find a way to measure these non-functional features. And then we somehow benchmark these features and evaluate. And the evaluation is not against some expected results because for these non-functional features, most of them cannot be captured by the system output. So instead of checking or validating against expected outputs, we we evaluate the results based on some predefined criteria according to the non-functional attribute. So this is an overview of system testing. And talking about functional or non-functional attributes or features, let's think about an example with what we may have seen every day. So the tram system here in Sydney. So you can see that there's a keyword test in this photo here. And for functional features, let's think about two scenarios. So the first one is we can test the tram scheduling feature of this entire system. So this is considered a functional feature of this entire system because the tram scheduling is like a main functionality of this system, right? So this is why it is considered as a functional feature to be tested. And another functional attribute is to test is the passenger information system. For example, we can see some information with some screens inside the cabin of the tram, and we can verify that whether the displayed information is accurate or not. So this is also a function of this system. So this is considered, if we test this system, then it's considered as a functional system test. And let's think about some non-functional features. And one example is about scalability. So for example, during some events or festivals, there could be more passengers than normal, right? We may schedule or we may allocate more trams during that period of time. So we can test whether our system is scalable enough to handle more passengers during events or festivals. And this scalability testing is actually considered as non-functional because it is not related to the key functionality of the system. So scalability is a property that is good to have, but it's not something that is a must to have feature for this system. So it is considered as non-functional. And another thing is we can also test for maintainability of this system. So we can assess whether it is easy for us to to do maintenance tasks. For example, here we are maintaining the road maybe, so we could assess how easy it is for us to do maintenance. And this maintainability is another example of non-functional properties we are interested in for testing. So as you can see here, normally functional attributes or functional testing are more specific to the system we are testing right now. So if we test some other systems, we couldn't, there's no such thing called a tram scheduling or passenger information system, right? We are testing different other features. But for other systems, there could also be scalability and maintainability, right? So for non-functional attributes or non-functional features, they could be different system could have similar attributes or properties. So this is an example of functional versus non-functional for system testing. So given the definition and an example of functional versus non-functional testing, let's consider whether security is a functional feature or non-functional feature in software systems. I'll give you some time to finish. So security, whether it is a must to have thing for software or not. Is it related to the functionality of the software or not? So let's have a look at the results. So actually the correct answer is could be both because for most of the software we use every day, for many of the software we use every day, security is not a must-have feature. Like for example, for the calculator of the built-in calculator app within Windows, we don't really care about security. Security is not a feature for this software, but security could be a key feature for some software systems. For example, the firewall installed or the Windows default. They have a Defender app, and for these applications, security is important. And for web CMS, of course, security is important. So security could be either considered as functional or non-functional, depending on the software system we are trying to use. So here is a quick comparison of functional versus non-functional testing in the context of system testing. So functional testing is actually mainly about testing the functionality of the product, and non-functional testing is more about testing different quality factors. And most of the functional testing could be done during unit integration or system testing, and most of the non-functional testing are actually done during system testing. So these are the differences. And another key difference here is that normally for functional testing, we can just use one set of configurations to do this because we are only care about the business logic of the software. We don't need to care about different scenarios, different conditions. But for non-functional testing, because we are trying to cover different properties, and some of the properties may require some specific setup or specific environment for us to do testing. So the configuration could be different for different test suite for non-functional testing. And now let's introduce some concrete strategies or some concrete metrics for doing functional testing and non-functional testing. And for functional testing, one of the most popular or the most well-known technique for doing functional system testing is called model-based testing. So this is because in many of the software we are using today could be modeled, their behaviors could be modeled or could be captured by some models. And instead of testing the software just based on its implementation, we can test the software based on the models to check the behavior against the models we are trying to use. And these models could help us in both ways. The first thing is it can help us to design the test cases, and the second thing is sometimes these models could help us to verify that whether the program behaves normally or not. So here, what we mean by model is it is just an abstraction of the system we are testing or we are developing. So the advantage of using this abstraction here is that because we don't care about some of the details here, we can do some more powerful analysis, as we will see in our following slides. And these models could be derived from either specifications or source code. And so it means that we can develop them from both requirements and implementations. So talking about deriving models from requirements, actually we have learned one requirement-based model. Can you guys what is that model we have learned based on requirements? Or functional testing or black box testing. So what is the model we have learned? Yes, correct. Decision tables or cause effect graph is actually a model we have learned based on requirements. And we will see some other models here in this lecture. So here are some typical models you may encounter in some literature or in practice. So the first one is finite state machine. And most of the software systems we are using today could be modeled as a finite state machine. And this is especially useful when the system has well-defined states. For example, this is a finite state machine for the vending machine. So you can see that whether the system is locked or unlocked is related to whether we push the buttons or we have coins or we insert coins or not. So there are many systems could be captured by this finite state machine. And another typical example is the protocols we are using every day, like the HTTP protocol, the TCP protocol. These protocol implementations, they do have well-defined states. So they could be modeled as finite state machines, and we can derive test cases according to this model here to trigger different transitions to reach a particular state, or check whether our system enters an error state or not. So this model here could be used for both deriving test cases and checking the behavior of the entire system. And another model here, which is somehow similar to the finite state machine, is called Petri-net, and this is a little bit. This is not often seen in computer science, but it is very useful in information science. And Petri-net is actually good at capturing the behaviors of distributed systems or systems with concurrency. So Petri-net is actually made up of places and transitions. So you can see the circles are the places, and the rectangles are transitions. So we can reach from one place to another through some transition. And each black dot here you can see is actually a token we are carrying from one space to another. So these are so this model here it is good at capturing the behavior of you can see the transitions between spaces carrying some information. So this is more suitable for testing some distributed workflows or distributed systems. So these are some two typical models here, and we have a lot more models. So another model here is, so those two models are actually based on graph, and there are some models which are not based on graphs. For example, we have some text-based models, which is an example of them is context-free grammar. So context-free grammar is actually normally described like this. So we can define a grammar of what we are trying to test, and this grammar can capture the structure of the input, and normally this context-free grammar is used to represent some languages, whether it is a programming language or it is a domain-specific language. So because it is a grammar which can capture languages, it is good for testing compilers, interpreters, or some language parsers. And another example, non-graph based example is decision table. So it is our good old friend decision table. So decision table is good at capturing the rules, and each of the rule is actually made up of the effect, which is the final action of the system, and the input, which are considered as the causes. So this is good at capturing the logic between different inputs and between the input and the output. So this is decision table. And actually, there are some pitfalls when we are trying to design decision tables, and there are some pitfalls I observed from last year's assignment, and you can see that I skipped one of the pitfalls because you don't make this one this year, so it's good. So let's skip that one. But one of the pitfall I observed from the assignment is that some students just try to focus on the actions when they design the rules. So they don't, but actually when we design the rules of the decision tables, we shouldn't just focus on the final actions. We should also try to build up rules according to the inputs or according to the causes in the cause effect graph, right? So let's think about an extreme case where we have a very big Q&A system. You can consider it as a big AI system, which can take anything as input. However, it can only output yes or no. So the output is only yes or no. So if we just focus on actions when we design the decision table, then it's very simple. We just have two rules, one rule covering the yes and one rule covering no, right? But that is not the case because this is a very complex system which can take anything as input. And for example, it can take whether the question of whether COMP3142 is a good course or not. And it can also take the question of whether Sydney is in New South Wales or not. So these are actually two types of questions if we think about it. So COMP3142, whether it is a good course, requires us to reason, right? It is not something like a fact, like it's a bad course, it's a fact, it's a good course, it's a fact, it's no. It requires us to reason about it. So if we do this, although this is like a black box system for us, so we can think about the internals of this system that it may have some kind of reasoning system inside, right? So to deal with these type of questions. And for whether Sydney is in New South Wales or not, it is actually about checking against some kind of facts. And we may think that, okay, this system may have some fact checking system inside. So when we design rules, we should think about what could be the potential causes. So in this case, instead of 2 rules to cover yes or no, maybe we could design 4 rules, which can try to cover the reasoning type of question, causing yes and no, which can cover the fact checking system, which can result in yes or no as well. So when we design decision tables, we should avoid just thinking about the effects. We should also think about causes. And let's continue. There are some more models. So those are the previous those previous models, whether they are graph-based or they are not graph-based. Most of them they are dealing with the inputs, so they are not. We don't care about the actual implementation. We don't care. They are not derived from the code. And there are some other models which could come from code, which could come from the actual implementation of the program we are trying to test. And one of them is called Markov chain. And Markov chain is actually a probabilistic model that represents states and transitions with probabilities. So this is often used for fuzzing, which we will be using in our assignment tool. And why can we so Markov chain, as I just mentioned, is a model that comes from the source code. And why can we model a piece of code as a probabilistic model? So the thing here is like this. So assume that because most of the time when we do random testing, we are feeding some random inputs into the program. And if we feed a random input into the program, whether we can reach certain part of the program is actually related to some probability. So for example, here we have this program called crash me, and it has 4 nested ifs. Each one of the if condition will check the value of 1 byte of the string here. And if that byte matches a specific character, it will move on to the next level of the if condition. So whether we can reach certain level or certain statement here with a random input is associated with a probability, right? So this is why we can model a program as a probabilistic model. And that is because if we feed random inputs into a program, the probability of reaching a particular location inside the program could be calculated. And this figure here is actually a screenshot from a paper, and it is well calculated actually. So if you think about why the probability of reaching from the input to passing the first if condition is 2 to the power of -10, it is calculated like this. So first we need to make sure that we have selected the correct byte here, right? We have 4 bytes, so it is 2 to the power of -2, which is 1/4. We have this chance of reaching here. And we need to make sure that this byte is created correctly, right? And how many possibilities do we have for each byte? How many possibilities do we have? So each byte is made up of 8 bits, and each bit could be either 0 or 1, right? So we have 8 0 or 1s. So the probability of making a byte of guessing a byte correctly is 2 to the power of -8, because we have 8 0 or 1s. We make them all correct. So it's 2 to the power of -8. So we select the correct byte. We make that byte correct. So this will give us 2 to the power of -10. And do you know why the reason of staying here is for 3/4? Like the probability, you can see that this edge here is associated with this. Because if we are not selecting the correct byte, we will be jumping back, right? So this is actually related to selecting the correct byte. So because we need to select A here to move to the next stage, otherwise we will remain at this state. So the chance of staying here is that we select the other 3 bytes except for the second one. So it's 3/4. So the entirety of this program, if we feed it with a random input, could be we could calculate a probability for reaching a particular location in the program. But as you can see here, this is the calculation here is very costly, and it actually depends on the conditions inside the program. And normally, theoretically, it is possible for us to do this calculation, but normally we need to do an approximation of this. So this is Markov chain, and this is an example from this paper here. And talking about and after we learned the model-based testing, let's move on to some non-functional features that we could use for system testing. So, like I just mentioned, non-functional testing here in the context of system testing is not about structural testing. It is more about different quality factors we can use to evaluate the quality of the software. And it actually, compared with functional testing, it involves more time, effort, and resources to do. This is the key reason here is because we need to set up different configurations, and sometimes it requires us to set up a near real life environment, and the details could be related to the customer's hardware setup and many other information. So this makes non-functional testing a very tedious process. So normally when we do non-functional testing, we only need to care about these 4 types of resources when we test software. So they are CPU, network, memory, or disk. And this is from the textbook, which is quite old. And can you think about another example of resource that we would care nowadays? Another type of software here, or another type of resource here. Actually, that's GPU. So because now we are using AI everywhere, right? When we try to train these AI models, or when we are trying to use these models for doing inference, we may need to use GPU resource. So here, instead of using CPU here, I would rather call it computational resource. So we care about computational resource, we care about network resource, we care about the memory of the system, and we care about the disk usage, which is the storage of the system. So the first, so that's about what type of resources we care when we try to come up with the quality factors. And now let's come to the first quality factor we are we care about. The first one is performance testing. So for performance testing, we can consider these following metrics. So the first one is load testing. So load testing is to check how the system behaves under expected load conditions. So for example, normally here for classes in CSE, we could have some big cohort with like 8 to 1,000 students, right? So 500 is considered within the expected load. So we may test WebCMS by simulating whether 500 students are concurrently using it, whether it can handle or not. So this is called load testing. And we can also do stress testing. So stress testing is in comparison with load testing. Load testing is more about like the normal test case when we do boundary value testing. So it's like we test against normal conditions. But for stress testing, it's more about testing whether how the system behaves under some extreme conditions beyond its expected maximum load. So, for example, if a news website is designed for 1,000 users to use it concurrently, we can try to increase the user count to 10,000 and during a major breaking news and see if the website crashes or not. So this is about stress testing. And there are some other metrics for performance testing. And the third one is spec testing. So spec testing is a test how the system performs when there is a sudden increase or decrease in the number of users or required resources. So the difference between spec testing and stress testing is that stress testing cares about the final number or the overall number. So the overall number is beyond the expected number. And spec testing is more about the sudden increase or sudden decrease. It's more about the change of the resource usage. So it's more about sudden change in resource usage. And another example is like, for example, before assignment, we can suddenly increase the user account to, we can suddenly increase the concurrent access from the students. So we may have a sudden spike of 1,000 students accessing the system all at once. So this could be used for spec testing. So this value doesn't have to be an extreme value. So 1,000 is still considered as within the expected load, but it's what we care is about the sudden change here. And another example, another metric for doing performance testing is called endurance testing. So this is to ensure the system's stability and performance over an extended period. So normally, a piece of software is expected to run for a period of time, right? And we try to run it for a longer time and see whether this software can still perform normally or not. An example is, for example, we are actually recording this video using Microsoft Teams, right? What if we left this meeting open and have it record for like more than 24 hours? Will the system crash or not, right? And this is one example, and there are some other examples for, like for example, there are streaming services from Twitch or YouTube. So you can run them for an extended period of time and see if there are memory leaks or some other performance issues over time. And actually, some older versions of Chrome has on Mac OS has a problem of memory leakage. So I don't know if this is the case on Windows, but let me see. So Chrome actually has implemented a feature. I don't know if you have noticed or not, but let's have a look. So don't sign in. I don't know if. So you can see if you hover your mouse over something here, let's open another web page, which may consume a little bit more memory. So if you open a different web page, so you can see here, if you hover your mouse over the tab here, you can see that it will display the memory usage of this tab. You can see it's 365 megabytes. And this one here is much smaller because we are not handling some videos in the web page. This is simply a landing page. So actually Chrome has, if you left the tab open on Mac OS, and in some older versions of Chrome, especially when there are video or streams services on that web page, there could be, if you left it open for maybe more than 1 day, or if you just forgot to close that tab on your Chrome, you may have a performance issue for your computer due to the memory leak issue. So there could be such issues. So this is called endurance testing. It's more about testing, executing the software for an extended period of time. So apart from performance testing, we could also do scalability testing. So scalability testing is more about testing whether our system can scale up or down as per demand by adding or removing resources. So the key here is about adding or removing resources in our system to do the testing. So it's more about resources here. So an example is we can gradually, for example, let's assume we deploy an application in some cloud service, for example, AWS service, and we can gradually increase the number of the servers we have on AWS, or the number of the resources we have for these servers on AWS, and see if it can maintain the performance when the user number increases. And normally this is done for cloud services or the elastic instances. So for AWS, I believe that you may have heard about the term called EC2, right? EC2 is actually the full terms here are called elastic computing services. So because most of the cloud service, if we rent a server that is expected to host, for example, if we expect 100 users are using our service, but we don't know when will the 100 users use our service, then normally we don't need to rent a server that can fully support 100 users at most of the time. We can maybe, let's say, rent a server that has a resource to handle 5 or 10 users to use, and then the system can help us to increase, for example, the number of CPUs to handle the services or the requests from the users as the user number grows. So these cloud services actually they allow the automatically allocated resources. So we can try to increase the number of resources required to test whether and try to scale up and scale down the resources we have to see how the system performs. So this is about scalability testing. It's all about adding or removing resources in our system. And another metric is called usability testing. So usability testing is more about humans because most of the software are created for humans. And this is more about assessing how easily users can learn and use the systems. For example, if we have a healthcare app, we can give it to a group of doctors and see if these doctors can use this app easily to perform some actions or not. And this feedback could be used to improve the UI and UX design. And this is related to human-computer interaction. And another metric here is called compatibility testing. So compatibility testing is to ensure the compatibility between different components of the system and between the software system and the context or the environment it is running in. So an example is we can test a mobile app on different versions of Android system. Like Android, they have different versions, and we can also test whether how it performs on different operating systems and with different screen sizes or OS versions. So normally this compatibility testing is done for some software that could run on multiple different devices. And a typical example software that is mostly done, used for compatibility testing is actually web page we are using every day. So because most of the web pages nowadays, they need to be designed responsively. For example, if we can still use the web browser as example here. So actually Edge, Microsoft Edge is actually using Chromium. It's not developed on IE. It's actually the same origin from Chrome. So many features are similar. So if you click inspect, if you right click on any web page, you can see this inspect button here. And if you inspect, you can see many interesting features which you can use. And one of them is to toggle, you can see this toggle device emulation. So you can select different devices here and see how your web page looks on different devices. So most of the front end frameworks nowadays, they allow responsive design. For example, if I drag this, you can see the menu here is automatically hidden when the screen is very narrow here. So this is quite a good design. So this is an example of compatibility testing. So it can test whether a web page is compatible for different screen sizes. So that's compatibility testing. And there's yet another metric for performance for non-functional testing, which is called availability testing. So availability testing is to verify the system's availability or uptime under specific conditions or during a period of time, and then we can measure the downtime as well. So, for example, we can test an online booking system to ensure that it has a 99.99% of availability rate which means that there's only 0.01% of time, which is when the system is down. So on average, that means only about 40 minutes of downtime per year. So this could be useful for some services. So for example, Google service might have some downtime, right? So we need to test the availability of the software by calculating its uptime and downtime. And the last one here is called reliability testing. So remember, the purpose of doing software testing and quality assurance is to ensure the reliability of the system. And here, the reliability is defined as the system could perform normally and consistently during the period of time when we are observing it. So the key here is about this defined period. So during a period of time, this system has no problem, then we can say that, okay, the system is reliable during that period of time. So what we can do is we can test a system and observe it for a period of time and see whether there's errors and crashes observed during that time. However, this reliability testing, as you can see here, all the other metrics are related to a particular property of the software. And reliability is more about, like observing the system during a period of time. And this actually overlaps with other functional testing, because when we are observing whether there are problems or not, we can observe for performance issues, we can observe for downtime, uptime, and all those kind of things. So this has actually, this reliability testing, actually it overlaps with some non-functional testings, some other testing metrics. So here is the overlapping between reliability testing and some other things, some other types of non-functional testing. So, and before we have a break, let's do a live poll and to practice or exercise what we just learned. So, which non-functional testing techniques are these two example requirements related to? So the first one is the query of 1,000 records should have a response time less than 3 seconds. And the second one is 25 clients login should be possible in a configuration that can only take 20 clients. So have you done? Okay, let's check the results. Okay, most of you can do it correctly. So the correct answer is load testing and stress testing. So I could see that this is what I expect actually. The second most choice here should be scalability testing. So we need to, so what's the difference between scalability testing and stress testing? So they are all about testing the system with some extra number of required resources, right? So the difference here is about whether do we increase or modify the resource we have in the system. So if we do a scalability testing here, what we need to do is not only to observe whether the 25 clients should be handled or not, we should try to allocate the system with more resources as more clients comes in. So So scalability testing is more about managing the resources or dealing with scaling up and scaling down the resources in the system. So because we are not trying to modify the resources here, so that's why this is only a stress testing. So we're not doing scalability testing here in this example. And now let's have a 10 minutes break. So, all right, let's start the second half. So, uh, we just covered the different functional and non-functional system testing in our first half of today's lecture, and that marks the end of levels of testing. So now let's move on to another topic, which is related to test automation and scaffolding, which is also related to how do we do testing during the process of software development. So by now we have covered many techniques to derive test cases for different targets, right? So we learned black box and white box techniques to derive test cases, and we learned how do we identify different targets for testing. But how do we actually, we have the targets, we have the test cases, but how do we run them? And we should run the code, and if we can run the code and check the results manually. So we can feed the inputs to the targets we have manually and observe whether there are problems or not. But please don't do this in practice because humans are slow, expensive, and sometimes error prone. And testing design actually requires effort and creativity as you may have experienced in assignment one. And the design should require effort and creativity, but execution should not. So we should somehow automate the execution of the test cases on our targets. So this is about test automation and scaffolding. So test automation is actually about developing some piece of software or some useful scripts that can do the execution or the repetitive tasks from do them for us, and so that we can focus more on the creative aspects of testing, like how do we design the strategies. So automation actually controls how and when these test cases are executed. So basically it takes care of the environment and preconditions of running the program, and it can also help us to automatically compare the results to check whether there's an error or not, and it can also helps us to automatically re-execute some failed test cases. And test scaffolding is actually a set of programs that is written to support this process of test automation. And it is normally not part of the product, and it is often temporary. So test scaffolding is like, how do we create some helpers or aiders for us to do test automation? And this is a typical structure of a piece of test scaffolding code. So we can see that the entire thing here, the entire thing is called a harness. So a harness is like a substitute of all of a part of the deployment environment. It actually depends on whether we use all the deployment environment or part of it depends on the unit we are testing. So basically everything here combined together, they are considered as the testing harness. And we have learned driver and stub in our previous lecture, right? Can you still remember what is a driver and what is a stub? A driver is like one layer above the target unit we are trying to test. So since it is one layer above, it actually provides the context or the environment for us to run the target unit, right? So a driver is like a substitute of a main or calling program for the target. So it prepares the environment for the target. And a stub is like one layer below the target unit. So it is actually a sub-component of the target unit we are trying to test. So a stub is a substitute of the system functionality that hasn't been implemented or integrated for testing yet. So both of them could be mocked up to prepare the environment for testing for the program unit to run properly. And then since we need to execute the program, we need to find bugs. We need to know whether the output of the program is expected or not. So we need to have a piece of output comparison code. And this output comparison code is also known as test oracles. So basically, an oracle can tell us about the future, right? About what will be expected. And it's similar here. So we can use some expected outputs of the program to do the comparison here and see whether the program behaves normally or not. And normally we can use assertions to do this output comparison. And in some cases, we also need to have this piece of tear down code. So tear down means any steps that must be taken after we run a particular test. For example, we may have created some temporary data in the database, or we may create a temporary file when we prepare the execution for this program. Or maybe this program, the target we are going to test, can modify the database, or it can modify some files. So we need to reset the system state before we run the next round of test, right? Otherwise, the next round will be affected. So we need to also have some tear down logic here. So there are some frameworks for us to write the structures of to write the test scaffolding code. So they are so-called unit testing frameworks. But normally when we are talking about unit testing, when we are actually doing it in practice, we are actually doing integration testing. It's not just, normally we don't just test one single function when we write tests. So for different languages, they all have their own frameworks. For Python, we have PyTest, we have Node2. For Java, we have JUnit. For JavaScript, we have Jest, which you might have been using in 1531. We also have Mockito. And for C or C++, we have GTest. For Rust, it actually has a built-in testing framework. And Python actually also has a unit test library, which is also a built-in framework, but pytest is a little bit better. And we will be using pytest for our assignment 2 as well. So let's have a look at some concrete examples using some of these, some code from these frameworks. So for example, let's assume that we are trying to test the implementation of a small calculator program. And this small calculator program has an adder class, which just have a simple function that can add two numbers up and return the sum of these two values. And this calculator can invoke this adder function to calculate the sum of two numbers. This code is definitely not a good implementation of this function, but let's just use it as an example here. So what we can do is assume we haven't implemented the adder class yet. What we can do is we can create an adder stub, which will just return some number here to simulate the behavior of adder. Actually, with PyTest, with a plugin of PyTest, we can do better mockups, but we will learn that later. And let's assume that we can write the stub like this, and then we can do the testing like this. So now let's try to think about which part of test scaffolding does each piece of code correspond to here. So first, what is this adder stub? What is the corresponding component on the left? So obviously, as indicated by the name, is a stub. So sorry, there's something wrong with the animations. But anyway, so this stub is actually a stub, but this entire thing here is considered as the harness. So everything here basically is a harness. What about these two assertions here? What are they? They are just output comparison, right? That's very straightforward. And let's have a look at another example. So with JUnit, so this is basically a JUnit test case. And so with this JUnit, we are going to show you what is a tear down. So a tear down is basically, for this one here, is to release the object memory here. But of course, Java can do garbage collection automatically, but sometimes we can still manually do this tear down or manually release the memory of an object. And this is another example with G-test. So we can see that we also have all these kind of things. We have this setup, which is actually the entire thing is the harness. And we also have the tear down, which is to release the resource. And we have these output comparisons here. And that's all about the main content today. In order to practice test automation and test scaffolding, we are going to learn how to use PyTest in practice. And similar to how we learned the Python syntax, I've created a file that can help you to learn PyTest. And you can't see this file yet because it's under week 5 and it's not available to you yet. And I'm still improving this. So, but today we are going to cover the first few sections here, so it doesn't matter. But you will have access to a full version of this file next week. And so why do we need to learn PyTest? There are several reasons. So the first one is, the very first reason is that we are using Python a lot in this course. So let's use a framework in Python. And the second reason is that its syntax is very simple. And the assertion of PyTest is also can give us rich information. We will see later. We will see with some examples later. And it actually also provides us some fixtures which could be used to manage some environment setup when we prepare our test cases. And PyTest also has a very diverse and very useful plugin systems. And we are going to learn 2 plugins here. One of them is PyTest Mock, which can help us to create stubs and drivers. And another thing is PyTest Curve, which can help us to inspect the code coverage of our test cases. So the installation is just similar to how you install other PyTest, about how you install other Python packages. So what you can do is on your login server, on the login.cse server, what you can do is, can you see this? Okay. Let me enlarge the forms. Okay, I just enlarged the fonts, and let's start from scratch. So now you can see that I'm in this folder here, and there's only, sorry, and let me remove this. So there's only this one single Python file here. And what we do is, when we use Python, is a good practice to use virtual environments. And do you guys know virtual environments of Python? Yes. Okay, that's very good. That's very good. Actually, there are many virtual environment management software like Conda or something else. And if you are using, if you do some AI projects, you may have been using this a lot. But now let's just use a built-in virtual environment manager of Python, which is what venv module. And we just use this command to create a new virtual environment. So this -m here means that we are trying to invoke the virtual environment module. And the second parameter here, venv, is just the folder to to store the virtual environment. So let's just name it as venv as well. So let's create this virtual environment. As you can see here, now we have created a folder called venv. And how do we enter this virtual environment? We just need to run this. We just need to run the activate script under the bin folder of the virtual environment we just created. So we just execute this script. So this script is automatically created. And if you can see something like this, it means that in your command line or in your terminal, this means that you are inside a virtual environment. And the way of getting outside this virtual environment is also using another command, which is called deactivate. So if we just deactivate, then we just get outside the virtual environment. So these are some basic commands. And now inside this virtual environment, we can install the PyTest package. So using this pip install, we can just install it. So after that, we can verify whether it's installed by running this PyTest. Since I've just written a test file in this folder, it will automatically run the test I have written. So basically, as you can see in the test, I just write a test addition function, which will just assert whether 1 plus 1 equals 2 or not, and it automatically gets executed by the PyTest command. So these are some basic commands we can use to install and run PyTest. So this is an example, and like we just discussed, PyTest has the advantage of giving us rich information for assertions. So let's try to use one compiler as example here. So let's try to do this. So let's say we have this assertion here, which compares. I need to enlarge the font here. So basically, this assertion will fail because these two leads doesn't equal to each other. So this assertion will fail if we invoke this function. So if we run it, you can see that it just throws out an assertion error which is never catched. And this assertion can only tell us, okay, this assertion fails. So that's basically the information we can get by default from Python. However, if we do this with PyTest, let's try to create a file for this test list. I think there's something wrong with Vim here. Oh. Oh, okay, it's okay now. So let's run PyTest again. As you can see, it gives us where exactly the diff is. So we can get much more information from PyTest than the assertions of PyTest than the assert of the Python itself. So this is a difference here, as you can see. And that's one of the reasons for us to use PyTest, and there are many other reasons. And just now, as you can see, if I run PyTest under this folder, in this folder, except for the environment, I only have two files. Each one of them has only one function, right? If we have a look at these files, so we only have two functions here. And how does PyTest know that it needs to run these functions if I invoke PyTest here? So this is how it discovers test cases from the code from this folder. So it tries to find something. First, it will check through the file names. If the file name is something like test underscore something or something underscore test, then it thinks PyTest will think, okay, this file is written for storing some test cases, and then it will look for test underscore something functions inside these files, and this is one source of tests. And the other source is that it can also look for classes with the test prefix in the class names. So this is how PyTest can automatically discover test cases. And there are some useful command line flags for us to play around with PyTest. One of them is whether do we want to have quiet or verbose number or verbose output. For example, if we run PyTest with nothing, is by default it by default prints out a little bit more information than quiet mode. For example, if we run quiet mode, as you can see here, it instead of showing where the test case is from, it will just show one character per test case, and it will also omit some other informations like how many items it has collected, and some printing format will also be changed. And there are some other command line flags as well. For example, we can also use -k to run particular tests whose name can match certain expressions. And we can also try to run tests with some markers. So markers means we can use decorators to annotate our test functions, and then we can invoke these markers. We can test only the test cases with certain markers using this -m command. For example, just now we have two test cases, and let's try to mark one of them with a special mark. For example, let's say we can name it as maybe list. We can use -m list. Oh, sorry, we need to import. If we want to use this decorator here, we need to import PyTest first. So as you can see here, it actually give us this, but we also received a warning because this is like a predefined name in Python, so it actually warns us, but it still allows us to run this test, and you can see that it can select two items. However, one of them is deselected because we specified that we are only interested in the test cases which are marked with the decorator called list. So this is another useful flag for us to consider to use in practice. And we can also specify the max limit for failures. For example, if we have, like in some real projects, we could have hundreds of test cases. And if we are at an early stage of development, we may encounter dozens or even sometimes hundreds of failures when we run the testing. And we can limit the number of failures for us to see to minimize the effort of debugging the code. So this is to also avoid overwhelming the final output report. And there are also another useful flag that you may use, which is called --lf, which is to run the last failed test cases. So this is to automatically run for example, if we just run PyTest, it will run two test cases. And if we just run --lf, it will automatically rerun only the failed test case. So this can also help us because when we are doing the actual development, once we find some failure of the test case, we are going to look into our code and try to fix the error, right? And and once we fix the error, sometimes we are only interested in the field code. So this command can help us to speed up the process by skipping those past test cases. So this is the usage of LF, and it is often used together with this max field. If we set the max field to be 1, and then we can always test the single failure we are dealing with. So these are some useful flags, and normally for a Python project, this is how we structure our test suites when we use PyTest. So normally we just put everything inside a folder called tests, and then we can write our unit test. We can put all of them in one folder, and we can put all of our integration tests in another folder, and we can put some commonly used fixtures to we can use some commonly used fixtures in this conf test.py file, which could be used to develop test cases. And this conf test.py is normally used to store the fixtures, and fixtures are actually corresponding to the drivers and stubs, or sometimes the higher level of environment setup in harness. So these are all handled by fixtures in PyTest. So okay, that's let's cover fixture maybe in next week, and that's all of today's lecture. And before we end, let's have a quick recap of what we have learned in the last 2 hours. So, and also in the last few weeks. So we learned everything. We start from how do we design test cases or test suites with different strategies, with black box strategy, with white box strategy, and that is what we have practiced in assignment 1. And then we looked into, and that's about how we design test cases. And because we have a big piece of software, we need to identify the targets for testing from this software. So that's why we learn different levels of testing. And in our last lecture, we learned unit testing. And each unit is normally a function or a class and all its functions. And then because unit is not enough for capturing some of the failures, because some software failures come from the interaction between different functions or between different units. So that's why we need to do integration testing to try to combine different units together into some subsystems that could be tested. And for integration testing, it is all about how do we combine things together, and we can combine things according to functions, and we can also combine things according to code structures. For example, we can use call graphs, and if we combine everything together, if we put everything together, then we are doing system testing. We are testing the entire system as a whole, and for system testing, we can do functional testing, which is different from the functional testing we have learned before. The context here is functional testing means that we are focusing more on the actual functionality of the software. And for non-functional testing here, it means that we are caring more about the quality factors that could affect the final quality of our software. And for example, we can do some performance testing. We can do scalability testing. we can do availability testing, usability testing, and so on. So these are the non-functional testing techniques. And after that, we learned everything about how do we design test cases, how do we determine test targets, and then now we have test cases, we have test targets, but how do we execute them, right? How do we automate things? This is related to test automation. And in order to do test automation, we need to write some scaffolding code. And for this scaffolding code, we know the basic structure, right? We know what is a harness, what is a driver, what is a stub. And we also know that for every test case, we need to have some output checking component. And sometimes we also need some tear down code. And that's all about today's lecture. And thank you for coming on Friday and have a nice weekend. Okay, thank you.